Cypher equality misses partial names, and vectors are overkill for lexical lookup. Neo4j full-text indexes rank matching nodes before the graph traversal even begins. You'll see how to connect the pieces into a workflow that indexes text, ranks name matches, and follows links for supporting evidence. I'm Professor Pine, teaching search and IR with simple Python. Graph search usually needs two things at once. Find nodes that look like the query, and pull the connected facts that explain why those nodes matter. Exact Cypher equality breaks when users type fragments or introduce typos. Full vector search handles fuzziness, but it brings storage, embedding costs, and drift. A Neo4j full-text index sits between those extremes. It gives fast lexical ranking inside the database, and then you can follow graph links for evidence. We index node names and short texts so Lucene can score candidates. A query returns ranked hits, and then we follow about relationships to collect supporting topic nodes. That keeps lexical relevance and graph context together. We'll build a compact demo to prove the idea. Load a few doc and topic nodes. Create a full-text index. Compare exact match against a scored query, and then pass top hits into a traversal to show connected evidence. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we confirm the database is reachable before creating anything. This snippet opens a Neo4j driver connection and confirms the database answers a tiny Cypher query. Engineers building retrieval systems need a reliable baseline before debugging relevance, because connection failures can look like empty search results. GraphDatabase.driver creates the Bolt client. Driver.verify connectivity checks the server, and driver.execute query runs a minimal return query against DB. The OK value comes back from Neo4j as real query data, not a hard-coded flag. The visible output shows the local database is reachable before we create indexes or search anything. Next, we load a small evidence graph so search has something to match and traverse. This example loads a tiny Neo4j evidence graph with searchable doc nodes and connected topic nodes. Exact property predicates are brittle when users type fragments like graph or retrieval instead of the full entity name. The cleanup query keeps the demo repeatable. Then rows is sent as a Cypher parameter so the text data stays separate from the query. Unwind creates each doc. Merge keeps topic nodes stable. And about gives search results somewhere useful to traverse later. The visible output shows how many graph nodes were created for the retrieval baseline. Now we add the full text index so scoring is explicit and reliable. This code creates the Neo4j Lucene full text index over doc name and text properties. A full text index is explicit in Neo4j, so Cypher will not silently switch a normal match predicate into lexical scoring. Create full text index doc text indexes both dname and dtext, which lets one user query search entity names and short descriptions together. db.awaitIndex waits until Neo4j can actually serve the index, then show full text indexes checks the state. The visible output confirms the index is online before scored retrieval starts. We want to see the difference between exact equality and ranked lexical hits. This snippet compares an exact Neo4j property match with a scored full-text query. The exact match only succeeds when d.name is exactly graph, so it misses graphrag, even though the description clearly contains graph. db.index.fulltext.query nodes searches the doctext index and yields node plus score. Then the query orders by score and name for stable display. The limit option caps how many Lucene hits Neo4j returns, which can reduce downstream traversal work when many documents match. The visible output shows the exact predicate misses, while lexical search still finds the right candidate. With ranked candidates in hand, we collect connected facts that explain the hit. This example passes the best Neo4j lexical hits into graph traversal for evidence. Retrieval systems often need more than a matched node. They need connected facts that explain why a result is useful. db.index.fulltext.query nodes finds candidate doc nodes for retrieval evidence, and match immediately follows about relationships to topic nodes. The score stays in the results so the application can keep lexical relevance beside graph context. Then driver.close releases the Neo4j client. The visible output shows a ranked document, its connected topic, and the score that carried it into traversal. In practice, you can map this pattern straight into a FAQ or a knowledge base. Use doc nodes for the content, topic nodes for the structured facts. Keep the lexical score next to the graph context, and you get explainable matches without embedding overhead. This is a lexical-first stage. Lucene ranks name and short text matches, and the graph traversal brings in supporting evidence. Use this when you need good name matches plus connected context, and keep a semantic fallback for queries that need true meaning beyond surface text. Try tuning the Lucene scoring next. For example, tweak BM25 parameters, or add n-gram tokenization for partial name matches. Then rerun the pipeline and watch how rankings change. If practical retrieval techniques help your projects, subscribe and watch the IR videos.